Black Pearl Audio Papers presents
Section 6. Illustrations. To apply this folk theory to a science, we restrict the science to some suitably hospitable domain. We then associate terms within the restricted science with the central terms of the folk theory. We seek to identify causes and effects such that they are related by a suitable relation of production. Finally, we may seek particular patterns among the causal relations, such as those listed in Section 5. The way we make the association, just what counts as a relation of production, and the patterns we may find will depend upon the particular content present. If we are interested in weather systems, for example, we would not ask for dominant causes. Because of its chaotic character, the smallest causes in weather systems may have the largest of effects. The dome. A first cause. As an illustration, let us return to the dome considered in Section 3. This will illustrate both how the patterns of the folk theory may be fitted to the science, and how successful fitting requires a restricted domain. We shall see that expanding the domain can defeat the fit by embracing an evident failure of causality. The failure of causality arises specifically at time small t equals big T, when the system spontaneously accelerates. Before and after, the system is quite causal insofar as we can map the appropriate causal terms onto the system. To see how this works, let us assume for simplicity that big T equals 0, so that the system spontaneously accelerates at small t equals 0, and let us consider the sequence of states at small t equals 0.5, 0.6, 1.0 in the causal period. Neglecting intermediate times for convenience, we can say that the state at each time is the effect of the state at the earlier time and the force then acting. If we represent the state at time small t by the position r of t and velocity v of t, and the force at t by big F of t, we can portray the causal relations in a blob and arrow diagram. By chunking, we can identify the first cause. If, however, we extend the time period of interest back towards the moment of spontaneous excitation at t equals 0, we can find an infinite sequence of causes at times, say, t equals 1, 1/2, 1/4, 1/8, for which there is no first cause. We have already seen the reason for this in Section 3. The mass moves during the time interval t greater than 0 only, and there is no first instant of motion in this time interval at which to locate the first cause. Any candidate first instant t equals epsilon for epsilon greater than 0 is preceded by t equals epsilon divided by 2. Might we locate the first cause at t equals 0, the last instant at which the mass does not move? As we saw in Section 3, nothing in the state at t equals 0 is productive of the spontaneous acceleration. One might be tempted to insist, nonetheless, that there must be something at t equals 0 that functions as a cause. The result will be the supposition of a cause whose properties violate the maxim that the same cause always brings about the same effect. For the physical state of the system at t equals 0 is identical with the physical states at earlier times, t equals -1, t equals -2, but only the state at t equals 0 is, by a false supposition, causally effective, where the other identical states are not. The folk theory of causation can only be applied in hospitable domains. This difficulty shows that when we add the instant t equals 0, the domain ceases to be hospitable. Analogous problems arise in the case of Big Bang cosmology. The universe exists for all cosmic times t greater than 0, and its state at each time might be represented as the cause of the state at a later time. However, there is no state at t equals 0, loosely the moment of the Big Bang, and the demand that there be a first cause for the process must conjure up causes that lie outside the physics. Dissipative systems. A final cause. There are many processes in physics in which the final state exercises a controlling influence on the course of the process. In thermal physics, processes spontaneously move towards a final state of highest entropy, which is, in microphysical terms, the state of highest probability. Dissipative physical systems are those in which mechanical energy is not conserved. Through friction, for example, mechanical energy is lost irreversibly to heat. Such systems can be controlled by their end states in a way that merits the appellation final cause. Consider, for example, a mass sliding with friction in a bowl. As long as the initial motion of the mass is not so great as to fling the mass out of the bowl, we know what its ultimate fate will be. The mass may slide around inside the bowl in the most complicated trajectory. Throughout the process, it will dissipate energy so that its maximum height in the bowl will lessen until the mass finally comes to rest at the lowest point in the bowl. That ultimate state is the final cause of the process. It seems quite natural to assign that final state the status of final cause. At a coarse-grained level of description, the evolution of the process is largely independent of the initial state, but strongly dependent on the final. One may want to object that it is somehow improper to assign the term cause to this ultimate state, for it exerts no power on the mass in the way, say, that the earth pulls the mass down through a gravitational force. In my view, the objection is misplaced. It elevates a gravitational force to the status of a true and fundamental cause, while there are no such things. A gravitational force is a cause in the same way that heat is a material fluid. The generative powers of the reduction relation that confer the character of cause on it can be used equally to confer the character of final cause on the ultimate state of this dissipative process. Scope. The illustrations above and those earlier in the paper are drawn largely from the physical sciences, for there it is possible for me to give the most precise account of the extent of viability of causal notions. I intend and hope that the account will be applicable in other sciences, although it is beyond this paper to put my hope to the test. I expect that the character of the application may change. In the physical sciences, an important reason for choosing a restricted domain is to fence off processes that are acausal. A second reason, to which I give less attention, is that different domains manifest different sorts of causes. In this section, the first illustration manifests efficient causes, the second, final causes. I expect this latter case to be prevalent in chemistry and non-physical sciences, that the restriction to different domains will divide different types of causation, as opposed to fencing off acausal processes. So chemical potentials might appear as efficient causes in one domain of chemistry, and in another, equilibrium states might appear as final causes. Correspondingly, in biology, viruses and bacteria might appear as efficient causes of diseases, while adapted forms in evolutionary biology might appear as final causes. This concludes Section 6 of Causation as Folk Science by John D. Norton. Please stay tuned for the final section.